to the SEG Europe Regional Advisory Committee's webinar series, Geophysics for Today and Tomorrow. The SEG Europe Regional Advisory Committee and myself, Lori Whitesell, will serve as your host for today's webinar. Before we begin, the model for this webinar will be a short presentation followed by an extended question and answer session. During the question and answer session, if you'd like to ask questions, please raise your hand in the webinar interface, and I will adjust your settings to allow you to ask your questions directly to the presenter. Alternatively, you can enter your questions in the questions and answer box. Today's speaker is Deyan Draganov. He is an associate professor at Delft University of Technology in the Netherlands. He received his PhD in applied geophysics in 2007 from Delft University of Technology. Since 2004, Dr. Draganov has published 56 peer-reviewed papers and 2 book chapters. He is also one of the editors of the book Seismic Interferometry, History and Present Status, and Geophysics Reprint Series SEG 2008. In 2010, he received the Clarence Karcher Award from SEG. Between 2012 and 2014, Dr. Draganov, together with Professor Walkner, gave 2 times a day 2 courses on seismic interferometry for exploration and production as part of the SEG continuing education curriculum. In 2015, he also gave the SEG continuing education virtual course, Seismic Interferometry from Theory to Practice. He served as associate editor of Geophysics from 2006 to 2017, and as an assistant editor for Geophysics from 2017 to 2019. So without further ado, I bring you Deyan Draganov. Welcome.
Hello, everybody. Welcome to today's webinar, which is about exploration applications of seismic interferometry with active and passive sources. During today's webinar, first we are going to see a motivation of why to use something like seismic interferometry, and afterwards you will be introduced to seismic interferometry. After that, you will see 3 applications for mining exploration from Europe of seismic interferometry with passive and active sources. And at the end, we will sum up by drawing some conclusions. First, why do we need seismic interferometry and what it is? A seismic survey is normally done by placing an array of sources at the surface. Also at other places, we place an array of receivers. Then we ignite the sources one by one or simultaneously, and we record the reflection response from the sources and the subsurface at the receivers. Using the reflection response, which might look like this, if it is modeled, for example, we apply some velocity estimation algorithms and 3D imaging to obtain, as a final step, a 3D image of the subsurface. So starting with sources and receivers of the subsurface, at the surface, we want to obtain a 3D image information of the subsurface. But sources can be relatively costly, especially in some situations, and that's why we want to make the most of them and obtain a really clear image of the subsurface. Sometimes due to presence of noise in the data, our subsurface image is not that clear. It is actually obscured by the present noise. Because of this, it would be nice to have a method that can be used to obtain extra information, which means starting with the data that we recorded to obtain, for example, virtual source information at the positions of receivers where we did not have active sources, and use this information to clear our subsurface image of the undesired obscuring information. Another problem with the sources can be that they might not be that welcome everywhere where we want to have them, like this big vibrator, as you see here from a field survey where there was really little space to place it except on this football field. Or it might even happen that the sources cannot even be used due to difficult terrain conditions, while single station receivers are much more easily placed. Especially this can be the case in environmentally sensitive areas where the single station seismic receivers can be used with a really minimal impact, while the sources will have a much bigger impact. Because of this, it would be nice to have an alternative where we just have receivers and then using information that they record, for example, from subsurface sources, passive sources, we still obtain an image or 3D image of the subsurface, what we are after. So these both aims can be obtained using seismic interferometry. And seismic interferometry is the process of retrieving new seismic records from existing records that we have recorded. The retrieval process can be achieved using cross-correlation, cross-coherence, cross-convolution, trace deconvolution, or multidimensional deconvolution. And in the following examples, we will see applications by cross-correlation and by cross-convolution. Furthermore, for the retrieval, we can use recordings that result from passive sources like ambient noise or microearthquakes, or from active sources. So what we actually record in the field using dynamite, vibroseis, hammer, whatever is used. And in the following examples, we'll see both such applications. So how seismic interferometry is applied and what we require from it actually. We require, for example, 2 receivers, which should be surrounded by sources on a certain boundary DD. Then the theory states that if we correlate the recordings at the 2 receivers from each of the boundary sources, and then we sum or theoretically integrate over the different sources on the boundary, then we'll retrieve the Green's function between the 2 receivers at positive and negative times. What we see here as equation 1, this is actually a very or relatively simple expression, which is used a lot in the practice. But to use this relatively simple expression, we need to comply with certain assumptions, which we used to simplify the more complicated exact relation to this equation 1. And these assumptions are that the medium parameters must be smooth around the source boundary DD. We assume to have homogeneous medium at and outside the boundary DD, that the boundary DD is a sphere with a sufficiently large radius, and large here is relative to the wavelength, that we can apply high frequency approximation, and that the medium is lossless. So it's always good to keep these assumptions into mind when we apply seismic interferometry, so that we are not faced with surprises. And we'll come back to that with the examples as well. So this is how we want to have the geometry of the sources when the receivers are inside the complete medium. When the receivers are at the free surface, or the Earth's surface, what we normally have as a situation when we do seismic exploration, then sources are needed only along a semisphere inside the subsurface. This is physically explained by the fact that we can effectively look at the Earth's surface, which is a free surface, as a mirror, which mirrors the subsurface sources, and then we obtain effectively a closed surface around the receivers. How do we retrieve reflections, for example, between 2 receivers? So between the receiver 6A and 6B, we want to retrieve such a reflection from the bottom of the 3rd layer. To do this, we have to correlate the blue arrival as recorded by receiver B with the magenta arrival as recorded by the receiver at A. The cross correlation will effectively eliminate the common travel path, and that is the overlaying path of the coinciding paths of the magenta and the blue rays. And then according to the theory, we also have to make summation or integration. And then constructively to this reflection arrival that we are after will contribute sources inside the so-called stationary phase region, which is the region around the specular ray. And the specular ray is the ray that connects the receiver XA to the region of the sources. What you see here, the coinciding magenta and blue rays. That was for retrieval of reflections. For retrieval of surface waves, for example, we can apply the same principle. We want to retrieve the surface wave between a virtual source at XA and a receiver at XB. For that, we have to correlate the blue arrival recorded at XB, so such a surface wave, with the magenta arrival at XA. Again, the cross correlation will remove the common travel path effectively, so the coinciding rays. And then we have to sum over the sources in the stationary phase region. And you see here that they are marked by transparent ellipses. We see that we need sources at the surface, but also in the subsurface. Sources at the surface will mainly contribute to retrieval of the fundamental mode of the surface wave, while the sources in the subsurface along the boundary DD will contribute to the retrieval of the higher modes mainly. Well, with this short introduction to seismic interferometry, let us look at 3 applications. And the first one is exactly about retrieval of surface waves so that we can use them for suppression of the really recorded surface waves in the active data. And we'll see an example from Ludvika mines in Sweden. This application was part of the Smart Exploration project, which in this case aims to illustrate surface wave suppression in a fully data-driven way using seismic interferometry. Note that this application or this method was first proposed actually far back in 2006 by Donk et al., but applications are still rare, not that popular. So one of the ideas is to popularize this method because it can be very helpful, as I hope you will see in the following slides. The data that we used was actually recorded in 2016 along a crooked line with fixed geophone positions. The total length was 2 kilometers, 650 meters. 451 receiver stations were used, spaced at 5 meters, and 387 shot positions, spaced at 5 to 10 meters. The receivers were 10 Hz geophones, and as a source was used a 500 kilogram drop hammer. How we apply seismic interferometry for surface wave suppression? Well, we take the data, we do some pre-processing, which here is not shown, but you can see it afterwards, the details in article that I refer to in the following slides. Then we apply seismic interferometry by correlation, cross correlation, and then we retrieve an estimate of the surface waves. Then we take these estimated surface waves and adaptively subtract them from the original data with the surface waves to obtain a really data with surface waves suppressed. And this is indeed a fully data-driven methodology. Why did I say here that we obtain an estimate of the surface waves and not really the exact surface waves? And this is due to the assumptions that were made in the application, in the equation 1, to obtain equation 1, with which here we do not comply. What we saw a few slides ago was that we need, for a good retrieval of the surface waves, to have sources inside the complete stationary phase region, which is at the surface and also inside the subsurface. In reality, of course, what we have here, due to the fact that it's a 2D survey, so survey along a line, we have sources which are in line with the 2 receivers, instead of in the complete stationary phase region, which means that we'll have amplitude errors in our estimates. Furthermore, we don't have sources in the subsurface, which means that we will not be able to retrieve higher modes if they are present. Well, here you see the results. In the left, you see the original input data, the raw data with the surface waves in it. The red pointers show target mineralization reflections, which are really covered and totally obscured at some places by the present surface waves, which are here indicated by the transparent green. In the right panel, you see the result after surface wave suppression, where we see the target mineralization really clearly now interpretable. So it shows the good application and usage of seismic interferometry for suppression of surface waves. Also, we see that some surface waves are left, and that is a result of the fact that we are obtaining a surface wave estimate and not the real surface waves, just because we have only sources at the surface and not also in the subsurface. What we don't estimate, we cannot afterwards adaptively subtract either. Still, if we apply surface wave suppression to not only to this common source gather, but to all common source gathers along the line, then we can apply, for example, stacking, and then here you see the result, unmigrated stack section. In the left, you see applied directly to the raw data after some pre-processing, but with the surface waves present. And of course, what we expect from experience is that our image will be really obscured by the surface wave noise, which did not stack out completely. In the right panel, we see the stacked section after surface wave suppression by seismic interferometry. And we see clearly the target mineralization imaged, also deeper reflector, but also interestingly, a really clearly now interpretable shallower reflector, which here is nearly impossible to interpret. For a fair comparison, also you see here in the left panel now, the unmigrated stack section after applying frequency wave number filtering of the surface waves. This is a standard method, and when applied in a good way, it also results in a really good suppression of surface waves, as we can see here. So the target mineralization again is clearly visible, but we see also here and here typical artifacts from FK filtering, so such linear events. What we also see is that the shallow reflector is not that clearly interpretable as in the result after interferometric surface wave suppression. And overall, the image after interferometric surface wave suppression is a bit crispier. Let us now see another application of seismic interferometry with active sources, again to the same data from Ludwika mines, but this time for improving the first arrival picking. Again, this application was done as part of a smart exploration project where we wanted to illustrate improved first arrival picking, again using a fully data-driven method like seismic interferometry. And again, this method is not really new, even though newer than the previous one. It was proposed in 2012 by Bharadwaj and et al., but its applications are still not that popular. So again, here we want to popularize the method. How were we retrieving the surface waves for the previous example? Well, we were correlating the arrival at the blue arrival at XB with the magenta arrival at XA. That was eliminating the common travel path, and we were obtaining a surface wave estimate between XA and XB, and this is the result. In the same, so afterwards, we can actually apply the same step for all sources that are in line with the two receivers, and then we can stack the separate results, and in this way we will obtain a really strong surface wave estimate, which is a good thing for a good adaptive subtraction. In the same way, we can apply seismic interferometry to refraction arrivals that we have recorded. For example, if we correlate the refraction recorded at XB, so the blue arrival, with the magenta arrival, the refraction recorded in XA. The correlation process, again, effectively will eliminate common travel path. This is easily seen. So this is the overlaying path here. So the magenta overlays the blue. And if we, for the moment, assume for illustrative purposes that the medium is locally horizontal, for example, here, then also this ray will be equal to this one. This path will be equal to this one. And then the correlation process will completely remove them, and we will be left over as a result with the retrieved so-called virtual refraction. And why? Virtual, not real, because it's something that we cannot really record from an actual source at XA and XB. So this is something that we can apply not only for this source, but for N sources, which are in line with XA and XB, just like we did it for the surface waves. And then sum their separate results with the result that our virtual refraction will become square root of N times stronger. So we will improve its signal to noise ratio with a factor square root of N, which is very advantageous, of course. So how do we apply seismic interferometry? We take the data. We can do again some pre-processing. Then we apply seismic interferometry by correlation to obtain the virtual refractions. But this is not the end. Actually, what we want is to apply as a second step seismic interferometry by convolution to the original data and the virtual refractions to obtain super virtual refractions, which are actually physical refractions, but with much improved signal to noise ratio. And again, this is a fully data-driven method. How exactly we apply the second step? Well, we will see that in these following illustrations. Seismic interferometry by correlation, we saw, requires that the two receivers are surrounded by the boundary sources. For seismic interferometry by convolution, what we need is that only one of the receivers is surrounded by the boundary sources, while the second receiver is actually outside of the source boundary. So how do we apply the second step? So seismic interferometry by convolution. We have our retrieved very strong virtual refraction after the first step. Then we take this virtual refraction as retrieved at the receiver at XB, and we convolve it with a physical refraction from the raw data that we have recorded at XA from a source between the two receivers. The convolution effectively sums travel paths opposite to the correlation, which was subtracting travel paths. And then the result is a retrieved physical refraction between a source at XA and a receiver at XB and a receiver at XA. Note that if we go back again to this illustration, using source-receiver reciprocity, we can exchange the positions of the receiver at XA and the source. And then in this way, we can actually convolve the virtual refraction at XA, at XB, with the refraction from a source which is on one side of the two receivers. So that's handy to know in the field where we can choose which geometry suits us best. So after retrieving this strong physical refraction, which is called super virtual refraction in this case, we can repeat this process for all N sources, for example, which are between the two receivers, XA and XB, and all these sources, of course, should cause a recorded refraction at XA. Then, stacking their separate contributions, we retrieve a super virtual refraction with even further improved signal to noise ratio by square root of N. And this is the illustration of the application of this method with the data from Ludwika mines. In the left, you see the raw data with the first arrivals, which are clearly visible for the short and intermediate offsets, but the later offsets are not visible at all. And here, so here, actually I should show, these were the surface waves, of course, so here. And here you see just the peaked or supposedly peaked first arrivals, which we want to use, for example, for first arrival tomography. Again, we see here the till intermediate offsets, the arrivals clearly, but later on not. Here you see in the left their interpretation. We see first the direct arrival, first refraction, and then a later refraction. And the first two, the red and the blue first arrivals, are actually quite clear. So we don't need to improve their signal to noise ratio, but we need to improve the signal to noise ratio of the second refraction. And that's what we are going to do, applying super virtual interferometry. Here you see in the top left panel the raw data, and here in the bottom you see the result after super virtual seismic interferometry, where we have now improved really the signal to noise ratio along the complete line of the receivers. And then complementing this result with the already sufficiently strong direct and first refraction arrivals, we obtain the final result here for this shot position. We can do it for any other shot position along the line, as you can see here, and then as a result apply the first arrival tomography, which now is much easier to apply because we see what to pick. I'm not going to show the result of it. Instead, I'm going to show actually application of seismic interferometry for retrieval of reflections for imaging at the Herolekas mine in Greece using local microearthquakes, which means now you will see an application with passive sources. We saw before how we can apply seismic interferometry by correlation to retrieve the reflection response from the bottom of the brown layer, for example, between two receivers at a certain offset. We had to correlate the blue arrival at B with the magenta arrival at A, and then stack along the sources in the stationary phase region. In a similar way, we can actually retrieve a zero offset reflection at the receiver at XA, for example, like this receiver, like this zero offset reflection from the top of the brown layer. And we can do that by correlating this blue arrival at XA with the magenta arrival also at XA, and then summing over sources inside the stationary phase region. In the same way, we can retrieve a zero offset trace or zero offset reflection in this case at the receiver at XB. Note that in this way, we are obtaining a recording that in the field is very, very difficult, or if not impossible practically, to obtain zero offset direct measurement. While here we get it directly as a result, and then from passive measurements. What we also see here is that if the medium below the receivers is more or less horizontally layered, then the sources in the stationary phase region will be more or less, again, vertically below each of the stations. So now we'll see an application of this method to data recorded specifically for this application as part of Smart Exploration project in central Greece in the Herolekas mine. And there it was very difficult to use active sources because it's mountainous region. Actually, the first picture that I showed you in the motivation part was showing the mountains in Greece, and there going with sources like vibrators is only possible along a road, so not where we exactly want them. The survey was specially designed and used 129 three-component short-period stations. Each station used a geophone that had a flat response between 1 and 60 Hertz. The stations recorded continuously the ambient noise, including local seismicity, for 4 months. And using these 4 months of continuous recording, we were able to detect about 3,000 microearthquakes with a duration magnitude between -1.5 and 2.5. From these 3,000 microearthquakes, 954 are actually what is usable for seismic interferometry by autocorrelation. And what does it mean usable? As I said just 2 slides ago, it means that the sources are chosen, so in this case the microearthquakes are chosen to be more or less vertically below a nearest station, and that means that their epicentral distance from a nearest station is less than 5 kilometers. In the right, you see the 3D distribution of the chosen 954 microearthquakes below the stations, which are here. And here to the left, you see the epicentral distribution of the earthquakes, given here in colored dots, where the color shows the depth, and the stations are shown here as black triangles. So these microearthquakes were used to apply seismic interferometry by autocorrelation. How? First, we take the data, we apply some pre-processing, which actually is used to detect the earthquakes, to image the source or the hypocenter, and afterwards, using that information, we can choose those microearthquakes, 954, which give us a near vertical arrival at each desired station. And near vertical, in this case, meant that a ray connecting the hypocenter with a specific station had the inclination to the vertical of less than 20 degrees. From those arrivals from each of the chosen microearthquakes, we extract a window that starts just before the first P arrival and finishes just before the first S arrival. So we choose the P wave coda. And then we apply to this extracted window seismic interferometry by autocorrelation to retrieve, again, a virtual zero offset section. And here you see retrieved virtual zero offset sections along two of the lines that we chose, for example, from the complete 2D array. And you can see that in 3D sense, the imaged reflectors are really well continuous. Here in this final slide, you can see an overlay of one of the previous two virtual zero offset sections, given here as a wiggle plot, overlaid on an earthquake tomography velocity model, which actually was obtained using the earthquakes that were identified in this data set. This image here is given in color scale, and both of these results are also overlaid on a grayscale image, which shows result of reprocessing legacy data, which was shot there several years ago, and it used indeed active sources along places where they could be used. So the line is not really aligning, is not coinciding with the line where we have the zero offset section. Still, you can see that the coincidence of all three results is really good. For the deeper part especially, we see here a very nice coincidence of the wiggle and the image, also for this reflector as well, and for this reflector. For the deeper part where the legacy data cannot really give a good image, we see a very nice coincidence of the zero offset section with high and low velocity anomalies. What we also see from the zero offset section, so from the wiggles, is that we have a really high resolution information of the shallower part of the subsurface, which is not achievable in this case with the reprocessed legacy data, again, due to interference of surface waves and other noise. And that brings me to the conclusions. So in this webinar, we saw quickly that we can use seismic interferometry with passive and active sources to useful ends for mining exploration and actually exploration in general. We can, for example, apply seismic interferometry to suppress surface waves in the active data in the data-driven way. We can also apply seismic interferometry to the active data to improve the signal-to-noise ratio of first arrival for their improved peaking. And we saw that we can even apply interferometry with passive sources, local microearthquakes, to obtain directly zero offset sections of the subsurface, something that we aim for after processing steps like velocity analysis and stacking. In this slide, you see all the papers to which this webinar was referring to. So if you're interested, you can look up the details. And with this, I thank you for your attention. And now I'm ready to receive your questions, and I'll try to answer them.
Thank you, Deyan. Again, if you'd like to ask questions directly, please raise your hand in the webinar interface. And you can also add your questions to the question and answer box. All right.
So are there some questions? There should be, I expect.
They're all being shy.
No need to be shy, just try me with something. There are a lot of details that, of course, I could not mention because of limited time and not to cause everybody fall asleep. I hope nobody fell asleep during this webinar. So you can try to show that you were not asleep by a question.
Okay.
Yes. I see. Let me see if I can read it. Okay, I have a question from Reza Malekmir. How does multi-dimensional deconvolution works? Can this solve 3D issues? Actually, each of the applications can solve 3D issues if we record in 3D. Multi-dimensional deconvolution really solves other issues like assuming the medium to be lossless for seismic interferometry by cross-correlation, because multi-dimensional deconvolution takes intrinsic losses into account. Actually, also seismic interferometry by convolution takes them into account, but it has other problems, and that is, I mean, convolution, seismic interferometry by convolution and correlation have the problem of needing the different sources to illuminate the receivers in a homogeneous way. Seismic interferometry by multidimensional deconvolution does not require that. Actually, in the deconvolution process, it compensates, if we have a good sampling of the sources and the receivers, for inhomogeneous source illumination. So if you meant that as 3D issues, then yes, it can solve it. I have now another question from Andrzej Pasternaki. What was the way to choose good from bad earthquakes in the Central Greece study? The good earthquakes are the ones that, for each station, so for a station, the good earthquakes are those that are vertically below it, more or less vertically below it, which means that their hypocentra are within an angle of 20 degrees from the station, from the vertical, so something like this. Furthermore, the earthquakes were chosen in such a way that they are visible at most of the stations, so recognized as PNS wave arrivals at most of the stations. Otherwise, we designate them as low signal-to-noise ratio earthquakes, and we don't use them.
There's a question in the question and answer box. It says, can you comment on the virtual source technique that has been patented by Shell?
Yes, I think that was, you're referring to the virtual source method. At least that's the patent I'm aware of. And that method is somewhat close to the method of the surface wave retrieval. It requires to have sources at the surface and receivers, according to the pattern, in a subsurface well. It can be vertical, deviated, or horizontal. And then the method itself correlates the first arrival from the sources at the surface to the receivers in the well with actually arrival with all the arrivals. So in this way, actually, it tries to eliminate propagation between the surface and the subsurface well. Of course, and I'm saying here tries to eliminate because it eliminates kinematically propagation on some of the arrivals, but the amplitudes are still not correct. Of course, they have propagated through the surface, through the overburden between the surface and the well. So the amplitudes will not be absolutely correct. Furthermore, it suffers, at least according to the original patent, through possible non-physical arrival retrieval. And that can be all solved if we use, instead of seismic interferometry, by correlation, as according to the patent, if we use seismic interferometry by multidimensional deconvolution.
Okay.
I hope that answers the question.
We have another question in the question and answer box. For the ambient noise interferometry, are there some metrics to determine which events are usable?
If we use ambient noise, so first matrix is to choose carefully what we want to retrieve, and knowing the theory, then we can decide what noise we want to use for it. So if we want to retrieve surface waves, then we don't want to have reflections, for example. And normally then people try to remove strong other arrivals like earthquakes, and then to ensure a good illumination of the receivers between which surface waves need to be retrieved from all sides, they really eliminate strong transient arrivals and try to keep only the noise, with the assumption that the noise will illuminate the receivers from all sides. An alternative is actually to choose only parts of that noise which has arrivals, surface wave arrivals, which are more or less in line with the two receivers. So illuminating from a stationary phase region, the two receivers from here and from here. So that is a good metrics, and one can make automated methods for it. For reflections, for example, there are such methods to choose only body waves in the noise, because only body waves will contribute to the retrieval of reflections, and then the rest, the other parts of the noise are just not used. Is that answering the question? To a certain degree?
Well, we have another question. They said yes, you answered the question.
Yes, I see now. I clicked on the right button.
All right, yes. Great. So the next question, for surface wave interferometry, do you have to modify the workflow when the fundamental mode of the surface wave is not the strongest event?
Well, it's difficult to say. It depends on the sources. If we have active sources, then the fundamental mode hopefully will be the strongest. Normally it is. Sometimes it is not, though, and then we have higher modes. If we have only sources at the surface, as far as I'm aware of, there is no processing method so far that compensates for that. If we have also sources in the subsurface, then one can start applying processing steps based on the theory that we saw now to suppress the contribution of the subsurface sources and to leave the contribution of the surface sources to retrieve stronger fundamental mode compared to the higher modes. I hope that answers the question.
All right. I don't see any new questions. Guess we'll give them one more opportunity. to us. These are pretty good questions, I think.
Yes, they are. So people were all attent. Very good.
Yeah.
Thank you.
All right. I see no additional questions, so I guess with that, we'll wrap it up here. I'd like to thank you, Deyan, and thank all of you for attending the SEG Europe Regional Advisory Committee's webinar.
Thank you for the attention.
As part of our webinar series, Geophysics for Today and Tomorrow. Please look for our social media posts for next month's webinar. And this webinar, you can view it again on the SEG YouTube channel. And again, thank you all. Thank you, Deyan. Great webinar. Thank you. Have a great day.
Thank you.
All right.
Bye-bye.